to. So have your notes and your blue sheet. Okay, so the first one we're going to learn is the integral test. If possible, you don't want to do the integral test because it's one of the most lengthy tests that we do. So if you can use a different test, you want to. However, a key to knowing you're going to do the integral test is if you see something inside the series that looks like it'd be an easy integral to do. Would that be an easy integral to do?
Yeah.
Yeah. So that's usually a key that we're going to use the integral test. So if you want to write that anywhere, usually you'll want to do the integral test if the inside of that series looks like you could integrate it fairly easily. So I would have been impressed if you would make it. Recycle. Okay, so after we get that, like, when we say, yep, I want to try the integral test, before you can even do the integral test, it has to meet 3 conditions. If you don't show these 3 conditions and you try to use the integral test, you get no credit, okay? So you have to show these 3 conditions before you can do anything. The first thing you have to do is show that you're always getting positive outputs. So let's see, if I started at 1 and went to infinity, no matter what I plugged into that end, what would it always be? Positive. So you could tell me, in this case, for all n, let's see, what would make it a negative? For all n greater than -1, right? Well, yeah, because that would be a define. So just for all n greater than 0, would that work? 0 or equal to 0, I could say in that case, right? So can I just say greater than -1? That would work. All right. So for all n greater than -1, I'm going to have positive. And since I started at 1, that's okay. All right. So condition met. So you don't have to show. Not in this case. There's really nothing to show. Okay. I mean, you've stated, yeah, that's going to happen. Right? Yes, absolutely for that one. Okay, the next one says, is it continuous? So if I had something like this, I would have to say, well, n cannot equal what? -1. So this is continuous for all n not equal to -1, so we're fine. Does that make sense? Okay, the next part you're going to have to do is show that it's decreasing. The decreasing, again, you can either do what 2 things? You could what? Derive and show that you get a negative answer. Or if you're decreasing, you could show what? So that's one way to show it's monotonic or like decreasing. What's the other way? If something is decreasing, then the next term is always what? Less than. So we could say that the next term is less than or equal to the previous term. So we could use either one of those 2 options, whichever way you like. Yes? That's okay. Right. That's a good question. I'll think about that. Because you asked, like, if you just say constant. I'll think about that. Okay, good question. Okay, so this is the thing, though. Let's say that I have the first 100 terms, and I throw them aside, and I start with term 101. Okay? At term 101, I find the rest of that series is always decreasing, and I find that it's convergent. So I take that sum of the convergence starting at 101 on, and I add on the other 100. What happens? Does it diverge? You have one thing plus 100 more. Is it going to diverge or converge? Let's say that the 101 terms converge to 5. Okay? And ever get infinity? Will you ever get negative infinity? So it's going to always converge. What if I threw out the first 1 million terms and I started with 1,000,001? Okay? And I found that that converged. And then I added on the other million terms. What's still going to happen? It's still going to converge. What if the 1,000,001 terms diverged and I added on 1,000,000 more terms? Diverged. So this is the thing. Like, we just need to say that from one end forward, I am always decreasing. From one end forward, if I can get it to converge, I'm fine. Does that make sense? So somehow write that. So for some n, you want to say it in your words, but for some n on, for some n forward, okay? However you want to say that. Okay, so after you get these three conditions being met, then you're going to set it up as an integral. You're going to take your infinity, you're going to take your whatever your starting point is, like the 1, and then you're going to take that and make it into a function. So you're going to set it up as an integral, and then you're going to integrate just like you did in the last chapter. After you integrate, you're going to see if you get this to converge or diverge. If you get the integral to diverge, guess what the series does? Diverges. If you get the integral to converge, guess what the series does? Converges. Feel confident? Let's do one. So I look at this and I think, is that easy to take the integral of? Yes. So I want to do the integral test. Well, in order to do the integral test, I have to show three conditions. First condition, Joyce. Is it always positive? Yes. For what n on? Okay, so from n greater than 0, right? It's going to be positive. So we're good. Or you could have said, I'm fine if you say from n greater than or equal to 1, you're positive. Same thing. The numerator. The denominator is always positive, right? So the numerator is what I'm kind of seeing. So I don't care. You could have said it either of these two ways. I don't care how you write it. Okay? But remember, n's are just integers. So I'm not dealing with 1.1, 1.2. That's why I don't care which way you write it. Alright? Next thing you have to do, Shane. Alright, so if it's continuous, what am I looking for? Any discontinuities would be in the... Alright, so in the denominator in this case, so what am I going to say? N squared plus 1. And I'm looking to see where it's what? Does it ever equal 0? No. Will n squared ever equal negative 1? No. Okay, so it's continuous for all n. No matter what you plug in. And the third thing we have to do, Michelle, is what? Show if it's decreasing. So how can I show if it's decreasing? Michelle? Show something's always decreasing. Okay. You can derive it. You want to derive it? Sure, let's derive it. You want to do the other way, Darius? No. No. To show that something's always decreasing, you have to show for an infinite amount of cases. So you have to plug in every number starting from 1 to infinity. Let's derive. Alright, so let's take the derivative. So So if we you want to use x's or n's? N's? Okay. So f of n is n over n squared plus 1. Go find f prime of n. I'm going to cheat. I already have it done. So where is this negative? That's what you're looking for, because that would mean that f of n is decreasing. Tyler, where is this negative? Okay. So you set it equal to 0, and then what'd you do? So negative n squared is negative 1, n squared is 1. So I would think, instead of setting it equal to 0, I would look and see where is this less than 0. Does that make sense? So, let's see. I just have, oops, negative 1. So n squared is greater than 1. Right? So what can I plug in? Anything greater than 1, or anything less than negative 1, right? But less than negative 1, do we really care about? Alright, so we're decreasing for n greater than 1. Now, hold on, I thought I had to have it at least equal to 1, right? It started at 1, don't I need it equal to 1 here? No. It's what we kind of talked about, as long as it's from sum n on. I could have found this to be 10 in some cases. Even though I started at 1, that's okay. From sum n forward, I am always decreasing. Does that make sense? Okay, so we said that that's good for n greater than 1. We are decreasing. So we're good. Yes? Well, you have to, like, it would go like this. Okay. So we've shown the 3 conditions, so what do we get to do? Integrate. So let's set up our integral. We're going to go from 1 to infinity of n over n squared plus 1 dn. So if I did a use sub, what do I need in the numerator? 2, which means I'm going to have to multiply by 1/2. I've got an infinity sign, so I'm going to replace it with b. Oops. I just was doing that, Shane. All right. Give me a second.
Okay, quick question.
Yeah.
Can't you just do a use up and just not even have to write the or n squared plus 1 thing?
Well, if you're going to use you have to change your bounds. Yes.
Go back
That's fine. Then leave the bounds blank until you go back and replug. Or write what they're going to be if you're going to go back in and replug. Okay? And that can be your intermediate work. Just don't put this equals something like without bounds. Don't put that. Because this is not true. You have to get your bounds changed for it to be equal. So if you leave off the equal sign and go do some intermediate work, and then at the end, like, put this equals something, that's fine. Okay. Alright, this is the limit. Speed goes to infinity. The 1/2 the ln n squared plus 1. And I don't need absolute values because that's always positive. If you want to put them, great. From 1 to b. And what do you get out for that? Infinity. Anybody not get infinity? Your work?
No, so you basically take the limit right ln of infinity plus or minus ln of 2 or
1/2, yeah.
Yeah,
But
that would be okay.
Infinity minus the number is still infinity. Okay, so this tells me that it's going to diverge. So your original series diverges by the what? By the integral test. Okay, after that you're going to love this next one. There's no sarcasm, I promise. Okay, it's not sarcasm, I promise. Okay, so this is called the p-series. It's like, bro, yeah. Okay, so this is the p-series. So your p-series is if you can get it set up to 1 over n to some number. So if I had like 1 over n to the 4th, how could I rewrite that? Right? So I could rewrite that to get it into the p-series. Okay? So if I can get it 1 over n to a number, then I can do the p-series. The p-series is awesome. When your p is just 1, this is a special case called the harmonic series. So the harmonic series is when you just have 1 over n. And a lot of times students are like, does the harmonic series diverge or converge? The harmonic series is going to always diverge. How can you remember? Think of mnemonic device. You can think harmonic series diverge. Yes. There you go. Everybody else have one? You can all hear Darius say that when you're trying to remember. Okay, because this is important to always, because people are like, gosh, when P is 1, which way does it go? Okay, because this is one of the frustrating parts. Okay, well, don't share your dirty one, Kenny.
No. Nerd.
Oh,
Nerd.
Let's hear your nerdy one. Sorry.
No, like harp, like the strings. Like they don't converge. They they're just like they're lines. They don't converge. So they have to diverge.
What?
I don't get it.
Hopefully that works for you. I don't know.
I got you.
Okay.
Strings.
I like parallel.
Yes.
Okay, I got it. Okay, so however it works for you, this will help if you can remember harmonic diverges. So, the conditions for a p-series to converge are if your p is greater than 1. It's going to diverge when it's less than or equal to, that equal to part is the harmonic series, so less than or equal to 1, but still greater than 0. And you see like how people can forget where the 1 goes? Is it included here or here? So that's why if you remember, harmonic series diverges. That's when it's 1, it's in the divergent. Okay? Just trying to help you. Alright, so do the following series converge or diverge? Harmonic series. Okay, so that's this guy. So that diverges by the p-series. Okay? Artists. last one. 3. So what happens? Converges by the p-series. Done. Don't you love the p-series? Stop. I know, me too. That's all. Yeah. Some of you have seen that one. Where I like to start it off. Alright. Let's do our quiz. Oh, I gotta stop recording.
You recorded off subject.